Assalamualaikum. Hi everyone. For lesson 15 part A, we are going to learn about subtopic 9.2 photoelectric effects. Alright, let's first look at all the learning outcomes in the lesson 15 part A. A. Define the photoelectric effects. B. Explain the phenomenon of the photoelectric effects by sketching a diagram of the photoelectric effect experimental setup. C. Define the threshold frequency, work function, and stopping potential. D. Explain the failure of classical theory to justify the photoelectric effect. What is the definition of the photoelectric effects? The photoelectric effects is defined as the emission of electrons from the metal surface when electromagnetic radiation of enough frequency strikes on it. And a photoelectron is an electron ejected due to the photoelectric effects, or an electron emitted from the surface of the metal when light strikes its surface. Look at figure 1. This is a metal surface. All these red spheres represent free electrons, while the groups of green spheres here are nucleus. When electromagnetic radiation with enough frequency strike the surface of the metal, electrons are emitted. The electrons emitted here are called photoelectrons, and the phenomena of emission of this electron in this manner is called photoelectric effects. The next learning outcome that you are going to learn in this subtopic is photoelectric effects experimental setup. Figure A shows a circuit diagram for the photoelectric effects experiment setup. This circuit consists of an evacuated glass tube. In this glass tube contains a cathode as emitter or target metal and an anode as a collector. Also a power supply used to supply potential difference between cathode and anode. A rheostat used to adjust the potential difference between cathode and anode. A voltmeter used to measure potential difference between cathode and anode. And an emitter used to measure current flows in the circuit. When the tube is kept in the dark, the emitter reads 0, indicating no currents in the circuit. But when an electromagnetic radiation with enough frequency shines on this target metal, electrons are emitted. All these emitted electrons attracted to the anode, current flows, reached by this emitter. Let's have a look at figure B. The power supply now is reversed, in which cathode is connected to positive terminal while anode is connected to negative terminal. Figure C shows a graph of photoelectric currents I against voltage for photoelectric effect experiment. This graph can be divided into two parts, part A and part B. Part A before reversing the terminal. Cathode connected to negative, anode connected to positive. And part B when the terminal is reversed, where cathode connected to positive terminal and anode connected to negative. When the voltage equal to 0, the value of current flow in the circuit is equal to I0. There is still current flow in the circuit, even though the voltage equal to 0. The current flow in the circuit because the electrons emitted from the cathode are collected by the anode. As the voltage increases, the value of current flow in the circuit also increases. Up to a certain value of voltage, the value of current flow in the circuit reaches the maximum value. This is because all the emitted electrons from the cathode are collected by the anode. But when the voltage is reversed, the current flow in the circuit is decreases. That is because only the fastest electron still can reach the anode. If we increase the reverse voltage, the current flow in the circuit also decreases. Up to a certain value, the value of current equals to 0. Why the current flow in the circuit equal to 0? That is because all the electrons emitted from the cathode are totally repelled by this anode, which is now negative. At this moment, the reverse voltage is called Vs, where Vs is stopping potential.
Nine C. Define the threshold frequency, work function, and stopping potential. Okay, from Einstein photoelectric equation, E is equal to W naught plus Ke max. E is the energy of photon, W naught is the work function, and Ke max is the maximum kinetic energy of the photoelectrons. Okay, from this equation, so E is the energy of a photon is equal to HF is equal to Hc over lambda. So this is the energy of a photon. So let's write the metal target. Okay, and then from at the metal target, so we have a work function. Work function is equal to Hf naught is equal to Hc over lambda naught. Okay, what is the F naught? F naught is the threshold frequency. Okay, and W naught is a work function, is a minimum energy required to photoelectron to eject from the target metal. And then the electron will attract and move to the collector, so it will make the maximum kinetic energy, which is equal to half mv squared, or is equal to EVS, and Vs is stopping potential. Okay, from the maximum kinetic energy of photoelectron, Ke max is equal to half mv squared is equal to EVS. Okay, from the graph, we look at after is reversing the terminal, so it's a Vs. Okay, Vs is stopping potential. There's the minimum reverse potential voltage needed for electron from reaching the collector. Okay, this we get by using the conservation of energy, which is the loss of kinetic energy of photoelectron is equal to gain in the potential energy. And the equation is the maximum kinetic energy is equal to EVS. EVS is the electron times dengan stopping potential. Okay, this is a case if the function, okay, the frequency, sorry, okay, is larger than the threshold frequency. Okay, the frequency is from the energy of photon, and then is larger than the threshold frequency. So the electron will emit from the surface and then will accelerate to the collector. So in this case, where the F, the frequency of the photon is larger than the threshold frequency, so electron will emit, and the equation is HF is equal to work function plus dengan half mv squared. Okay, and then this, if the frequency of the photon is equal to the threshold frequency, okay, the electron is just eject from the surface, and no more, the electron will not move and attract to the collector. So K max is equal to 0 because V is equal to 0. Okay, and then when the F, the frequency, is smaller than the threshold frequency, so there is no electron will be eject from the surface. So to occur the photoelectric effect, so we have, it's a depend on the frequency of the photon. Okay, the application of photoelectric effect, so one is a solar panel, okay, and then another one is a night vision device. Okay, so now we look at the observation of the photoelectric effect experiment. Okay, number one, electrons are emitted immediately. Second, stopping potential does not depend on the intensity of light. 3. Threshold frequency of light is different for different target metal. And the fourth, number of electrons emitted depend on the intensity of light. Okay. Okay, dependence of photoelectric current on intensity of incident light. So this for the number of a photoelectron. Yeah. Okay, and then this graph is shows about dependence of kinetic energy of photoelectrons on the frequency of light. So the different target matter, so different threshold frequency, and then with the enough frequency of from the energy of photon, so the electron will emit from the target metal. Okay, this is for the a few different threshold frequency of light for the different target metal. Okay, this example. Okay, now 9.2D. Okay, explain failure of classical theory to justify the photoelectric effect. So there is a two prediction from classical prediction and modern theory. So we look at the first item is the maximum kinetic energy of photoelectron. In the classical prediction, okay, the higher of intensity, the greater energy in part of the metal surface for the emission of photoelectron. Okay, and then the higher of the intensity of light, the greater the maximum kinetic energy of photoelectron. This is a classical prediction. Okay, in the experimental result, where low intensity but high frequency radiation could emit photoelectrons. And the maximum kinetic energy of photoelectrons is independent of light intensity. So the modern theory, based on the Einstein photoelectric equation, the maximum kinetic energy is equal to HF minus work function. Okay, the maximum kinetic energy of photoelectron depends only on the light frequency, and the maximum kinetic energy of photoelectron does not depend on the light intensity. So the keyword is the kinetic energy is depend on the light frequency. Okay, the second one is the emission of photoelectron. Okay, it's about energy. Okay, in the classical prediction, emission of photoelectrons occur for all frequencies of light. Energy of light is independent of frequency. Okay, in experimental result, emission of photoelectrons occur only when the frequency of the light exceeds the center frequency, which value is characteristic of the material being illuminated. Okay, so in the modern theory, when the light frequency is greater than threshold frequency, a higher rate of photons striking the metal surface result in a higher rate of photoelectrons emitted. If it is less than threshold frequency, no photoelectrons are emitted. Hence, the emission of photoelectrons depend on the light frequency. Again, so in the modern theory, so the emission of photoelectrons depend on the light frequency. Okay, the third item, emission of photoelectron in terms of time. Okay, classical prediction, light energy is spread over the wavefront. The amount of energy incident on any one electron is small. An electron must gather sufficient energy before emission, hence there is a time interval between absorption of light and emission. Time interval increase if the light intensity is low. Okay, in the experimental result, photoelectrons are emitted from the surface of the metal almost instantaneously after the surface is illuminated, even at very low light intensity. So the difference is in time interval for the classical prediction. Okay, in the modern theory, the transfer of photon energy to the n electron is instantaneous as its energy is absorbed entirely, much like a particle-to-particle collision. The emission of the photoelectron is immediately and no time interval between absorption of light energy and emission. Okay, the last one is energy of light. Okay, classical prediction, energy of light depends only on amplitude or intensity and not on frequency. So is opposite with the expected result. Energy of light depend on the frequency. So in modern theory, according to the Planck's quantum theory, which is E is equal to hf, energy of light depend on its frequency. So this is a prediction between classical theory and modern theory. Okay, experimental observation deviates from the classical prediction based on the Maxwell electromagnetic theory. Hence, the classical physics cannot explain the phenomenon of the photoelectric effect. The modern theory based on Einstein's photon theory of light can explain this phenomenon, okay, photoelectric effect. It is because Einstein postulated that light is quantized and the light is emitted, transmitted, and reabsorbed as a photon. Okay, this is a summary how we comparison between classical physics and quantum physics about photoelectric effect experiment. So we look at a few features here. Okay, the first one is the threshold frequency. In the classical physics, an incident light of any frequency can eject electron. So it said does not have threshold frequency as long as the beam has sufficient intensity. But in the quantum physics said to eject an electron, the incident light must have a frequency greater than a certain minimum value, which we call threshold frequency, and no matter how intense the light. Okay, the second feature is the maximum kinetic energy of the photoelectron. So it's in the classical physics, it's depend on the light intensity. But in the quantum physics, the maximum kinetic energy depends only on the light frequency. Okay, the third one is the emission of photoelectron. Okay, there should be some delays to emit electron from a metal surface, but in the quantum physics, electrons are emitted spontaneously. Okay, and the last one is energy of light. So in the classical, it's a depend on the light intensity, and then for in quantum physics, it's a depend on the light frequency. Okay, question. Why classical theory failed to explain the spontaneous emission of photoelectron? The answer is classical theory predicts that the emission of photoelectron is not immediate and there is a time interval between absorption of light energy and emission. Okay, that's all for part A.